Mastering Automotive Cybersecurity. V2G and V2H connectivity is a ticking time bomb for transportation and energy systems. What are the potential cybersecurity implications and vulnerabilities that arise from vehicle-to-grid, V2G, and vehicle-to-home, V2H, connectivity, and what measures can their manufacturers and users take to identify, mitigate, and address them effectively to ensure the secure integration of these technologies into our transportation and energy systems? Vehicle-to-grid, V2G, and vehicle-to-home, V2H, connectivity have the potential to revolutionize the way we think about energy consumption and transportation. However, these innovative technologies also introduce a new realm of cybersecurity implications and vulnerabilities that must be carefully considered and addressed. One of the primary concerns with V2G and V2H connectivity is the increased attack surface area. With the ability to connect to the grid and home networks, electric vehicles, EVs, and charging stations become more vulnerable to cyber threats. Hackers may exploit these connections to gain unauthorized access to sensitive information, disrupt the power grid, or even take control of the vehicle. Specifically, some of the potential cybersecurity vulnerabilities associated with V2G and V2H connectivity include: 1. Unsecured communication protocols. V2G and V2H connectivity rely on various communication protocols, such as OCPP, Open Charge Point Protocol, and IEC 61850, which may not be adequately secured, allowing hackers to intercept and manipulate data. 2. Weak authentication and authorization mechanisms. Inadequate authentication and authorization processes can enable unauthorized access to EVs, charging stations, and even the power grid. 3. Inadequate encryption. Poor encryption or lack of encryption can allow hackers to intercept and access sensitive information, such as charging station credentials, vehicle identity, and location data. 4. Insufficient network segmentation. Failure to segregate networks and isolate critical systems can enable lateral movement in case of a breach, allowing hackers to access sensitive areas of the grid or vehicle systems. 5. Unpatched software and firmware vulnerabilities. Failure to regularly update and patch software and firmware can leave EVs and charging stations vulnerable to known exploits. 6. Lack of secure boot mechanisms. Inadequate secure boot mechanisms can allow hackers to introduce malicious code during the boot process. 7. Insecure data storage. Poor data storage practices can enable access to sensitive information, such as charging history and user data. To identify, mitigate, and address these cybersecurity implications and vulnerabilities, manufacturers and users can take the following measures. 1. Conduct thorough risk assessments and threat modeling exercises to identify potential vulnerabilities and prioritize mitigation efforts. 2. Implement secure communication protocols, such as Transport Layer Security, TLS, and Secure Sockets Layer, SSL, to encrypt data transmission between EVs, charging stations, and the grid. 3. Implement robust authentication and authorization mechanisms, such as multi-factor authentication, to ensure only authorized access to EVs and charging stations. 4. Implement network segmentation and isolation techniques, such as VLANs and VPNs, to prevent lateral movement in case of a breach. 5. Regularly update and patch software and firmware to prevent exploitation of known vulnerabilities. 6. Implement secure boot mechanisms, such as UEFI Secure Boot, to prevent malicious code from being introduced during the boot process. 7. Implement secure data storage practices, such as encryption and access controls, to protect sensitive information. 8. Establish incident response plans and conduct regular security audits to identify and address vulnerabilities. 9. Collaborate with industry stakeholders, government agencies, and cybersecurity experts to stay informed about emerging threats and best practices. 10. Develop and implement comprehensive cybersecurity standards and guidelines for V2G and V2H connectivity, such as the SAE J3016 Standard for Cybersecurity Guidebook for Cyber Physical Vehicle Systems. 11. Educate users about the importance of cybersecurity and provide them with resources and guidelines to secure their EVs and charging stations. 12. Implement secure firmware and software update mechanisms to ensure that updates are secure and do not introduce new vulnerabilities. 13. Conduct regular security testing, such as penetration testing and vulnerability assessments, to identify and address vulnerabilities. 14. Implement intrusion detection and prevention systems to detect and respond to cyber threats in real time. 15. Establish information sharing agreements and threat intelligence platforms to share threat information and coordinate responses. By taking these measures, manufacturers and users can effectively identify, mitigate, and address the cybersecurity implications and vulnerabilities associated with V2G and V2H connectivity, ensuring the secure integration of these technologies into our transportation and energy systems.